Hello and welcome to our lecture on inferential statistics. In this particular lecture, we're going to be talking giving you more of a motivation for why we need inferential statistics, and we'll be talking a little bit about what kinds of problems you can solve using this technique, using these techniques, and where you would apply it and when you would apply it. In the subsequent lectures, we will talk a little bit about how you would apply it and also why you do some of the math that you do, why you do some of the computation. So understanding it a little bit more on the nuts and bolts level is something that will follow. But in this lecture, we're going to focus on why you need inferential statistics in the first place. And we're going to do this through the lens of something called hypothesis testing. So hypothesis testing is a very widely used and accepted tool for a lot of data analysis, and if you understand inferential statistics through hypothesis testing, many other concepts in inferential statistics just fall in place. So things like confidence intervals and so on, which you might have heard, become fairly easy to understand and process. So having said that, let me jump into the subject. The idea behind inferential statistics is to make some inference about the population from the sample. Just to jog your memories, I think we've spoken about population and sample a couple of times, but this is different from what you would have done with descriptive statistics. Right? With descriptive statistics, you don't care about population or sample. In the end of the day, you had some data set, and for simplicity's sake, assume that was a sample that you got from population. And this sample, you were very content in descriptive statistics with describing that data set, with describing that sample, in case you had a sample. But here, the kinds of problems that you're more interested with inferential statistics are ones where you have a population and you're getting just a sample from that. But from this sample, I don't want to just say something about the sample. I don't want to talk about the mean of the sample. I don't want to talk about the variance of the sample. I don't want to talk about centrality, dispersion. My goal is to say something about the population. I only have data, which is the sample. I don't have the data associated with the population. But with this sample, can I say something about the population? So that's the core idea. And just to kind of jog some of your memories, the idea behind population and sample is fairly simple. We've looked at it with a couple of examples, but you can think of the population in one of two ways. The first and the more obvious way is that there exists this really large data set associated with a phenomena. So let's say the phenomena was the height of all boys who are in 10th standard in public schools. So that could be a very large data set, and let's say that was for India, right? So it's a very large data set. There are a lot of children who are in the 10th standard who are in public schools across India, and you could think of that as the population, and you want to say something about that population, and you might not have that data. So you go take a sample. So you select 5 schools or 10 schools, or you select 200 students through a census process randomly and take that as a sample. So you've taken a sample of some subset of students from the population. That's one way of thinking of population sample. And another way could be that the population itself is more of a theoretical, abstract concept. So you could not have an actual data set, but it could be something like, I've created this new machine, and this new machine is going to start making certain products. And let's say you're very interested in the product dimensions. So let's say the diameter of a product this machine makes. So you put in raw material into this machine, the machine spits out some finished product, and this finished product should have a diameter, has some diameter. Here, you don't, because it's a new machine, you might not actually have a population that is a really large data set that exists somewhere. The population here is the concept that if this machine were to create infinite such products without any change in time or space, the dimensions of these products would be the population. And ultimately, you might say, hey, let's just, for the first time, run this machine and make 10 products, and these 10 products that I physically have and I've measured and so on is the sample. So here is a case where I still want to use the sample to say something about the machine in general, not just the 10 products the machine has churned out, but the concept of a population here is not an actual finite large data set in my hands. It's more of a concept. Okay. Now, having revisited population and sample here, let's again say the statement, which is that inferential statistics, you want to say something about the population from the sample. Okay, so as I said, the major aim of this lecture is to motivate you to see why inferential statistics is important. So I felt that the best way to, for instance, do that might be to give you some examples. So that's what we're going to do. And I'll start with some simple examples. I've broken them down into one sample and two sample examples, and pretty soon that will become clear what that distinction is. So let's start with the first example, which is a one sample example on the upper left of your screen. So the idea here, and just so you know, we're in this part. The idea here is that let's say we were interested in noting the average phosphate levels in our blood, and I don't have a medical background or anything, so don't look at the medical aspect of this example, but let's say that your doctor or doctors in general, or public health advocates say that the average phosphate levels in blood should be less than 4.8 milligrams per, I don't know, deciliter. So again, irrespective of the unit, so the whole idea is that this number, which you can get if you go measure your blood, should be on average less than 4.8. The key here is an understanding that this should be less than 4.8 on average. So that means the doctors or the public health advocates understand that sometimes it could be greater than 4.8, and that perhaps in this particular case is not a cause for alarm. Again, don't focus on the medical aspect. I don't know if it is or not, but this is the situation I'm creating, right? So, but the important thing the doctors have told you is that on average it should be less than 4.8. Okay, so let's say you say, and there's obviously variation. So it really depends on what you ate that day. It depends on what time of the day you take the measurement. It depends on what instrument you use to take the measurement. It depends on how much water you had. So let's say there are a lot of factors that you don't seek to control, and that's the whole idea behind this. But you want to take a set of measurements. And you want to take a set of measurements and answer the question as to whether the average phosphate levels in your blood, in general, right? Not just on the sample that you've taken. The sample could be anything, but you care about, in general, is my average phosphate level in blood less than 4.8. So the question might arise, why are you distinguishing between what the sample says and what reality is? And that's going to become clear in a second. So let's first go about trying to answer this question, right? So the first thing is, if you took a set of measurements and let's say you got consistently very low values. So let's say you got 2.4, 2.5, 2.1, 2.7, 2.3, 2.9. Fill up 4 more numbers in the 2 points, okay? Then I guess you really don't need a statistician, right? You can look at that sample that you've got and you can say, look, I'm fairly certain that even if I went on taking more and more samples, or that if I woke up another day, threw all this data out and took another sample, or if I took infinite many samples, in either case it looks like my average is going to be less than 4.8. That's fine, intuitively that seems obvious. Similarly, the flip side, suppose you were to take this data and you consistently got 5.5, 6.1, 7.7, 6.9, and so on, where every single data point is significantly greater than that 4.8 mark and approximately in that same region, meaning it's not wildly moving around, right? So that's also an intuition that you might have, that if 1 second it's 6.5 and the next second it's 2.1. It's wildly moving around. But here I'm giving you examples where it's 6.1, 6.7, 7.1, 7.3, 7.4. So it's consistently significantly greater. Again, you don't need a statistician. Somewhere your intuition, you just say, look, I mean, based off of the sample, I'm willing to bet that my average phosphate levels are less than 4.8 mg per dl. But then it gets a little tricky. What happens if you had numbers, some of them below, some of them above, right? So some of them are less than 4.8, some of them are greater than 4.8, and in some sense, what do you do then? And the instinct or the intuition there sometimes is to say, well, let me take an average of the sample, right? If that average is greater than 4.8, then perhaps I should conclude that my average is greater than 4.8. And there's a small problem with that kind of an approach, right? I mean, assume that you got the readings like such as 5.1, 4.8, 4.9, 4.7, 4.7, 5.3, 4. And you got some set of readings and you took the average, and that average was 4.85. Okay, so you're saying, you know what, the sample showed that it's greater, and you conclude, for instance, that the average phosphate level in my blood in general is greater than 4.8 based off of the sample that I just saw. The problem with that could be that maybe if you just took 2 more data points, let's say you took 2 more data points, you increased your sample by 2 more, and you got a 4.6 and a 4.7, and all of a sudden, because of these new data points, your average slides just below 4.8, right? Something about doing this process where you just take the average of the sample and make a conclusion does not seem correct for this reason, right? And another way of looking at it is also that we've looked at this notion of sampling distributions, right? So we know that let's take a look at that same graph that we looked at the end of last class, right? So you had this thing which we described as the original distribution, okay? And let us just say for now that truly this distribution, by the way, represents the amount of phosphate in mg per dl that you will see in your blood if you do a test at any given point of time. So you get numbers from this distribution. So sometimes you get a 5.1, that's the dot there. Sometimes you get a 4.4, that's the other dot there. But in the end of the day, it looks like on average, right, given how I've drawn it, on average it's only 4.7 mg per dl, which is less than the 4.8 mark that we were interested in. Now you go and take a sample, right? This is the same example as the last time. So you took the sample and you got some data points. So you took 6 data points and this is what you got. Now if I were to just take the sample average, and I'm just eyeballing it here, if I just took the average of these numbers, right, I would say that average falls somewhere here, wouldn't you say? So this might be the average of these numbers, or maybe it will fall right on this dot actually. So let's say this is somewhere out here is the average, and the truth is the sample average is greater than the 4.7, and if we were to just go by the sample average, we might have concluded that the amount of mg per dl is greater than 4.8 or whatever, right? But here's the good part. You've now had a class in statistics that told you that the average that you get from the sample is not always going to fall on this 4.7, right? As your number of samples tends to infinity, yes, it will converge to this point, right? But if you've got a finite number of samples, and that's not right, so it is not going to always be exactly on 4.7. So what is it going to be? What it is going to be is another distribution, right? So if you had n samples, and this distribution will change with more samples, if there are many samples, then literally, if as the number n tends to infinity, this distribution will pretty much lie flat on this line. But if not, you're still getting the sample mean. The mean that you calculate from the sample is literally a random variable that you're getting from this distribution. So it's literally like you just picked a random point from this distribution, right? So you could get a point anywhere here. You probably won't get a point here, right? Because it doesn't. The probability of getting this point from this distribution is very low, is almost zero. So you will be getting points from this distribution, and as a result, just because this number is greater than 4.7 should not make you conclude that this mean, which is what you're trying to conclude. You're trying to say something about this line. You're trying to say something about this line, which is the mean of the population. And because you get a sample mean, which is nothing but a number from a distribution, should not make you conclude that therefore it is greater than 4.8. Okay, so that's why you need to do something more. You need to do something more complex than just blindly taking the sample average. Okay, so again, we're going to talk later about how you do it, but and what and when you do. But right now, I'm just trying to motivate for you why you need something else. Okay, so take another example, and in this example, we take a problem of proportions. So let's say the health department or some dentist related body says only 5% of the toothpastes of any given brand can be out of specification, right? So out of specification might mean that you have some ratings on amount of fluorides toothpaste can have. So let's say you're allowed only 1,000 parts per million of fluoride, and there are other chemical limits, but the health department understands that not every toothpaste can match exactly the ideal requirements. So let's say they set out limits on the chemicals, and they say, look, if you're a toothpaste manufacturer, I'm going to only allow 5% of your toothpastes to be out of specification. 95% of your toothpastes that I see in the market need to fall within my guidelines. Okay, same problem comes up again. You can take a sample of 10, 20 toothpastes, right? And it could very well be that truly this toothpaste brand is involved in a chemical process or a manufacturing process that creates on average only 4% of the toothpaste that this company makes, okay, are actually out of specification. But it's perfectly possible that you went and took 10 toothpastes from the market, and your luck, right, 7 of those 10 are out of specification. That's perfectly possible, right? It might not be the most probabilistic thing, but it's perfectly possible. It's possible that this toothpaste company is involved in a manufacturing process and a chemical process that creates toothpastes, and on average 4% of all the toothpastes they make. So when I say toothpaste, think of it as a toothpaste tube. On average, 4% of all the tubes they make have a chemical composition that is not acceptable. Okay, which is fine because the health department says you can't go more than 5%, and this toothpaste company is raising its hand and saying, hey, it's only 4%. But I now go and randomly sample 5 toothpastes, 10 toothpastes, and I find that out of the 5 toothpastes that I randomly sampled, 3 of them are defective. All of a sudden I'm saying 3 out of 5. That's 60%. You say only 5% is allowed, and I find 60%. And so does that mean the company is not creating toothpastes less than 5% rate, which are in conformance less than 5% rate? Probably not. Again, you need a little bit more nuanced thinking, and you need a little bit more statistics to actually answer this question. based off of the sample. You can't just take the sample average. Um, Another example, the third example that we have in the one sample case is, imagine that you are an insurance company, okay, and you find that there is this particular mechanic shop, like a garage, which does repairs, and because most people are required to have insurance, once the garage kind of writes out an invoice, and people who file the insurance claim attach this mechanic's invoice and tell the company to reimburse them for these for this rectification that's done to the car. And let's say this is a new garage, and the insurance company is suspecting that these guys are cheating, that they're set up as a place to not do any real work but just write really high invoices so that the insurance company so they're involved in some kind of a fraud. So one thing that the insurance company can do is saying, okay, I'm going to look at the next 10, 20 or whatever repairs. So let's say up to this point this garage has not made a single claim, but it's just being set up. But the inside word is that they're trying to they're trying to cheat the system. So once the garage gets set up, this insurance company is ready. The first 10 claims or 20 claims that this garage files, or 30 claims, they take those claims and they see how that compares to the national average in terms of average claims, right? Again, the problem is, just because this sample is greater than the national average, can we conclude, yes, these guys are cheaters? And just because the sample average is less than the national average, can we conclude these guys are not cheaters? And the answer to both those questions is no. Right? In some cases, like when I was talking to you about the phosphate, it might be brutally obvious, right? Where every single data point is so high or so low that you're like, I don't need a statistician to tell me that the answer to this question. But when it's not that case, you need a little more. You need inferential statistics to answer that question. Okay, so we looked at single sample cases. By that we essentially mean that there was one data set and you were essentially comparing that data set to some benchmark number that you had in your head. Let's now move to two sample situations. Okay, the example here is, let's say that I am running a foundry and some guy comes in, a consultant comes in and says, if you change the temperature a little bit of the molten metal that you're pouring in or whatever, let's say he says change the temperature down by a degree or two, and I assure you that the average number of defects that you'll see in your metal cast will decrease. So it's like a mechanical engineering application. You're like, okay, maybe the consultant knows what he's talking about, but how do I test it? And the answer to that question is, you can do the following, which is, before you go change things, you can measure the average number of defects in your casts, and you do that for 10, 20 data points. Okay, and then you do what the consultant says, which is to change the temperature, and then you collect another 10, 20 data points. Now let's go back to the question. If the average of the first sample, so now you have sample A, sample B. Sample A corresponds to before the temperature was changed, sample B corresponds to after the temperature was changed. Now obviously, in all likelihood, there's going to be some average to sample A and there'll be some average to sample B. In all likelihood, these two are not going to be the same. One is going to be higher or lower than the other, right? Just like in the single sample case, if they're so dramatically different, these samples, and when I say dramatically different, I mean dramatically different with respect to some amount of variability there is in the two samples as well, then you don't need a statistician to tell you. It's like so obvious that changing the temperature dramatically reduced the number of defects, right? But in many cases, you don't know. And in those cases, it's not obvious to say the average of sample A was different from the average of sample B, right? Go back to, I'm going to erase this, but erase the red ink, but go back to this example. Let's say that this is the original distribution of the number of defects. Okay, so this is the original distribution, and let's say this is 3 defects and this is like 9 defects. No, that's too high. Let's say this is 5 defects and this is 1 defect. So this original distribution is what I care about, that goes from here to here. These are the number of defects you will see in a cast. Okay, now obviously if I take a sample of 6 or so, I get a random point. Let's say this is the random point I get. Okay, I'll erase the other one. Okay, done, erased. So I basically I took the original distribution, I took a sample of 6 casts, and when I take a sample of 6 casts, like we discussed, the average is not going to always be exactly 3. It's going to be some number that falls into this distribution, the distribution of sample means, and I've drawn a random number that I got out here from that distribution. Okay, so good. Now let's say that this consultant who was telling you to go increase or decrease the temperature was completely wrong. Let's say he had no clue what he was saying. He was just lying. But fortunately or unfortunately, whatever he said does not make a difference. I mean, he lied in that, you know, he said it's going to improve the process. It did not improve the process. Luckily, it didn't make the process worse. Okay. Now you go take, and because the process has not changed, the original distribution has not changed. Now after the temperature is changed, the number of defects you're going to receive are also exactly in conformance to this distribution. It's in conformance to this outside distribution, the original distribution. Right? So that hasn't changed essentially. This mean hasn't changed. Okay, this mean hasn't changed. Now you go take a sample of 6. You get another sample average. And this sample average again is going to belong to this distribution. And let's say this sample average was this value. Okay, so this is the new sample average. So this is new. Okay, so that's new. Now you can't say, hey, this new sample average is higher than the old sample average, therefore the population mean is different. It's not. I mean, I just gave you an example where the population mean truly did not change, but how you could have seen 2 different sample averages and concluded that one is greater than the other. So this is why, again, you need more than looking at the sample average of A and sample average of B and saying, hey, one is higher than the other, so we should believe that what the consultant said was correct. Or the other way around, you know, if you conclude that what the consultant said has definitely made things worse, that's also not correct. It's perfectly possible that there was truly a change, but because of luck, you know, you saw things the other way around. Another example you can think of, and the next example is one where I wanted to emphasize variation rather than just the mean. Let's say you have 2 different manufacturing processes, and you want to compare their variance of the finished product in each batch. So you have manufacturing process A, manufacturing process B, and they make batches of finished material or finished product, and within each batch there's some amount of variance of each product. That's some amount of variance, right? Variance is the inherent variation between one part to the next. And let's say I care about that variance. Let's say I don't, in a particular batch, I don't want one product to look very different from the next product. I don't care about the mean, but I want them to all be consistent. Again, you would use the same concept. You would take the first batch, which is made from machine A, calculate the variance of it, calculate the variance of that sample, take the second batch made from machine B, calculate the variance of that sample, and again the overarching concept exists. You can't just say sample variance of machine A is lower than sample variance of machine B, therefore I conclude that machine A is better than machine B. It's perfectly possible that machine A is actually worse than machine B, but because you ultimately only have a sample, that machine A got lucky. Ultimately, it goes back to this idea that you see in this distribution, that sometimes you get a number on this side of the distribution, sometimes you get a number on this side of the distribution. The more data points you take, the overall variance of this distribution reduces, which is why if you had infinite number of points, right, none of these problems exist, but you don't. And if you're dealing with that, then the right thing to do is to use inferential statistics to look closely at the data. Another example that is often quoted is things like are 10 standard girls taller than 10 standard boys in India. For instance, we all know that in terms of average heights, men have larger average heights than women, but we've also heard that girls start growing taller earlier. So I don't know, is 10 standard a break-even point? At least some statistics textbooks seem to think so. So you could have a simple question like the population here is 10 standard girls in India, 10 standard boys in India. You're ultimately taking a sample, and based off of that sample, what can you say about the population? And sometimes the story is obvious from the sample itself. Sometimes you need inferential statistics to come in and tell you whether you can say something concrete, or perhaps you cannot say anything concrete, and that's also something inferential statistics will tell you. But ultimately it's not as simple as just saying the average of sample A is greater than average of sample B, and therefore I'm going to conclude one way or the other. Okay, so let's go to what it is that we will be trying to do with inferential statistics. I'm just going to go through the overarching principle, and keep this in mind. We'll revisit this slide a couple of times, but I think the ultimate test in some sense of you understanding what it is and how it is and why it is will really become clear once we do the actual math with each test, and ultimately these will come in the form of tests. I mean, some of you might have heard of these tests like t-test, z-test, chi-square test, f-test, ANOVA, and so on, and we'll go through each of these tests, but here is the overarching principle with respect to hypothesis testing, right? It's to have a null hypothesis and an alternate hypothesis. So for instance, in the fluoride case, the null hypothesis could very well be let me erase this. The null hypothesis could very well be that you have less than 4.8 mg per dl. So the null hypothesis is that the actual phosphate levels, the average phosphate levels in blood for person X is less than or equal to 4.8. And so the alternate hypothesis would be that it's greater than 4.8, right? The important thing is the null hypothesis and the alternate hypothesis in some sense together should be mutually exclusive, right? Which means that if it's greater than 4.8, it can't be less than or equal to 4.8, right? And vice versa. And collectively exhaustive. They should essentially cover the entire space that you're interested in talking about. So I mean, meaning that the average phosphate level is either less than or equal to 4.8 or greater than equal to 4.8. It can't be neither. So it's collectively exhaustive. Okay, so then what we will be doing, and you've not been taught this yet, but you will be doing some basic calculations or arithmetic on the data to create a single number called the test statistic. So you don't know what that is yet, but what you'll do is the reason I'm explaining this to you is to give you an idea that you are going to be working with the sample. So it's not like magic in that you're not going to say something about the population without dealing with the sample. So you will be doing some math, and some of that might involve taking things like the sample mean, the sample standard deviation. But you'll be doing some math on that, and when you finish with that math, you'll be getting something called the test statistic. Some of you might have heard of these test statistics. They might be called the Z statistic or the T statistic, and so on. The crux of null hypothesis, the crux of hypothesis testing is that if we assume the null hypothesis to be true and make some assumptions about distributions of various variables, and those that we won't go into that much, but if we assume the null hypothesis to be true, then technically the test statistic should be no different than drawing a random number from a specific probability distribution, right? So in some sense, right, what we're saying is if the null hypothesis is true, if the true mean, right, is equal to 4.8 this time, because the null hypothesis is true. The null hypothesis was, is it less than or equal to 4.8? So here the null hypothesis is true. So let's take the extreme case. The true mean is 4.8, And let's say there are some assumptions like that this distribution is normal, maybe that the samples that you're taking are independent of each other. There's some set of assumptions that you take. If all that of it is true, then we want to do certain things such that you will get another new distribution. You'll be doing some math with these data points. See these data points that you got from the sample? You'll be doing some math with those data points. You'll do that math such that the test statistic would be no different than a single random number that you draw from a very specific probability distribution. If that is the case, then you test the probability that the test statistic you calculated belongs to this theoretical distribution. Right? You basically say, hey, it looks to me like if the null hypothesis is true, then whatever I've calculated out here with the sample should be like drawing a random number from this distribution. So let me calculate the actual test statistic and see how likely it is that this number came from that probability distribution. And that is what we call as a p-value. Now, once you have done this process, you might say, look, if the null hypothesis is true, then the test statistic that I should have calculated should have come from this distribution. But look at the number that I got in my hand. It's so unlikely that I could have gotten this test statistic from this distribution. Therefore, the null hypothesis perhaps was not true, and I'm going to reject the null hypothesis. Or in some cases, the test statistic that you get looks like it does belong to this distribution, this specific distribution, and therefore you cannot really say anything. It's like you just have no grounds for rejecting the null hypothesis. You can just say I fail to reject the null hypothesis. The important thing for you might want to take a look at this procedure a couple of times, but the important thing that you might want to digest from this is that the p-value itself is associated with the probability of seeing this data if the null hypothesis were true, and not really the probability of this hypothesis being true given the data. So it's probability of data given hypothesis, not probability of hypothesis given data. So I hope that kind of clarifies inferential statistics for you. And in the next class, we will look at some specific tests and go over how you actually do these tests, and even go deeper and talk about why we do some of the mathematical operations that we do. Thank you.